Hello, this is Devi Patel and Quincy Nielsen's glider project.
Okay, so the requirements for this project were that it had to fit within a 16-inch by 16-inch box, it had to fly at least 20 feet, and it had to be propelled by a hand throw and also have no sharp points so that it wouldn't hurt anyone.
With our brainstorming process, we first noticed that the wings should be tapered and turned up based on research we have done, and that there should be a decently large horizontal and vertical stabilizer. And because balsa wood is so light, we would have to add additional weight in the center of the wings in order to counterbalance horizontal and vertical stabilizer. Other ideas we had were swept-back wings to put the weight on the nose in case the stabilizer was way too heavy, and if the glide was not long enough, to add more height to the stabilizers.
So for our initial design, we wanted to make sure that it was as stable as possible, and we learned about stability in the dynamics and controls assignment and also from our research. So we learned that we wanted the weight of our glider to be centered around like the middle of the glider, and that the wings should be closer to the nose than to the tail. And we also made sure that in our design there were no sharp edges, and so that it wouldn't hurt anyone when we threw it. This is the side view of our initial design, and this is a top view.
These are a couple of our first flight tests. This one showcases the initial design and how it immediately crashed because there was too much weight in the front. And this one was our farthest test flight with the plane going 25 feet and us putting the weight now in the front of the plane and the wings now being swept back. It went much farther once we made those changes.
So this was our final design for the glider. You can see it in a 16-inch by 16-inch box, and this was as it looked on the day of the tournament.
Our best test flight took place at the tournament with the plane going 27 feet.
To estimate the lift and drag coefficients, first starting with lift, we estimated it to be 3.29, and we calculated this by multiplying our angle of attack in radians by 2 pi. We estimated that our angle of attack was about 30 degrees. Then to find the coefficient of drag, we used the formula shown on the slide. We calculated the area of our wing to be 31 inches squared, and we estimated the E constant to be 0.8.
In conclusion, we learned about how weight distribution affects flight greatly. When our initial design was back heavy quite a bit, so the plane would fly directly upwards and then crash back down, only going about 2 feet. So through this process, we learned how adding weight to both ends causes a better flight. If we had more time, we would have worked on a more efficient weight distribution, experimented more with wing sizes and shapes, and work more on stabilizers. And these are the sources we used.